So we are going to talk about Chapter 8 first, and Chapter 8 is covering sampling distributions. So you may have heard of sampling distributions and have an idea of what that means, but we'll talk about that again. So sampling distribution represents a distribution, like a normal distribution, or you have uniform distributions. Now a sampling distribution is where the distribution, each value contained in this distribution is a sample. So we spoke about two different type of sampling distributions back in Matthew 43. That being the mean and the proportion. And so the sampling distribution of x bar would mean that each value in the sampling distribution of x bar is a sample mean. So for example, let's just say, that's section 8.1. We talk about the sampling distribution. So section 8.1 is the sampling distribution of a sample mean. Okay, so when we talk about a sampling distribution of a sample mean, that means every single value in the in the distribution is an x bar, because that would be a sample mean. So for example, let's just say that we have an original distribution, because we always take a sample from an original distribution. Let's just say that we have a normal distribution. So let's just call this the original distribution. The original distribution is normally distributed with mu equals, let's just say 100, and the standard deviation being 15. So each tick mark would represent 15 up from mu or down from mu. So this would be 85, this would be 70, this would be 55, and this would be 115, 130, and 145. Now if we were to take a random sampling from this distribution, let's just say of size n equals 4. Let's just make this easy at first. N equals 4. So we're going to take a random sampling from this original distribution of size n equals 4 and figure out what the average is of that sample. So let's just say x1 bar, representing the first sampling from the original distribution. Let's just say we get so since we know that a normal distribution is have a heavier mass towards the middle and lighter towards the tails, we would expect most of the values. So I'm kind of just making this up. Let's just say we have 102, 87, 105, and 97. So we just gathered a sample of 4 from the original distribution. And actually, so to be more exact, this would be the, let's just call this sample 1, S1. Sample 1 contains 4 different values, and then x bar 1 would be the average of those 4 values. So in this case, that would be equal to 102 plus 87 plus 105 plus 97 divide 4. So I will go ahead and calculate this really quickly. And so that would be 97.75. So this 97.75 is our data value. This is actually just the first data value that we found in this sampling distribution. So we have a sample size of 1 from the sampling distribution, where each sample, in order to find our x bar, is size n equals 4. So we've only gathered a sample size of 1 so far of this sampling distribution. Now let's imagine that we just gathered another sampling of size 4. We'll call this S2, and 88, 94, 102, and 121. And so this, from the second sampling of n equals 4, we have just determined that the average is adding them all up, 88 plus 94 plus 102 plus 121, and divide that by 4, is 101.25. Okay, so we have two values in our distribution, 97.75 and 101.25. Now let's just imagine that we continued this process, and let's say we have x bar 3 and equals, let's just say we gathered another size of n equals 4, and that ended up being 98, and then x bar 4 equals 105.5, and then we continue this process, and let's just say we do a large number all the way to x bar 1000. So we've gathered 1,000 different x bars. So that means we have 1,000 different values from the sampling distribution. So as soon as you get to a large sampling size of 1,000, of where each x bar is determined by an n equals 4, then what we essentially have like every single value that would be in this distribution. So what we'll notice is the shape of this distribution will be skinnier than the original distribution that we gathered our sample size of n equals 4. It will be slightly skinnier. And the reason I say it's slightly skinnier is because we only gathered a sample size of n equals 4. And now, hopefully, you're kind of getting an idea of what a sampling distribution represents. We have an original distribution. We're going to gather a sample from this, and to kind of get an idea of what this sampling distribution shape is, we need to imagine that we're gathering a large amount of x bars of size n equals 4 on each x bar, and that will give us a rough shape by plotting on these 1,000 different x bars. So all these values right here are x bars. They're sample means of size n equals 4. And what we'll notice is that the mean of this distribution, I'm not running out of room, I'll just say mu, we denote this in the book, mu of x bar, that is technically, by the law of large numbers, we know that this is approximately equal to mu. So that's something you may have remembered from section 8.1, back when you took Math 243. Now 8.1 is section 1.1 in the 244 text, the RCC custom version. So this is equivalent to 100. And you may also remember that that the standard deviation of the sampling distribution of x bar, so you may remember that the sampling distribution of a sample mean we use the subscript of x bar to represent the whatever parameter we're looking at, in this case mu of x bar, and sigma of x bar, the standard deviation of x bar, the mean of x bar. And we're talking about the shape of the distribution of plotting all these points. And you may remember that this is equal to sigma. In this case, we chose sigma to be 15. Now that would be sigma divided by the square root of n. Now n is not 1,000. 1,000 represents kind of taking a large sampling, so we have the shape of this distribution. N is actually how many values we gathered in each sampling, which is n equals 4. So I'll put n, but that is equivalent to 15 divided by the square root of 4. In this case is equivalent to 7.5. Now I mentioned it's a skinnier distribution, and that you may remember from Math 243, it's because of this relation of sigma divided by the square root of n. As n increases, that means your distribution is skinnier and skinnier as n increases, so compared to the original distribution. So this is just kind of a general idea of how we build a sampling distribution to visualize a sampling distribution. So let's go ahead and try to practice a problem. So I'm going to look at a problem from the text, and let's go ahead and look at problem 10 from section 8.1 or 1.1 from the custom text. So, problem 10, it asks you to determine mu of x bar, sub x bar, and sigma of sub x bar from the given parameters of the population and the sample size. So, problem 10, we're given that mu is equal to 64 and sigma is equal to 14. Okay? And we also know that n is equal to 36. So based off this information and understanding what we just did on the previous page, we can visualize what's going on here. These are the parameters of the original distribution. So this is the original distribution in which we're taking a sampling from. And the sample size that we're taking, so each sample in the sampling distribution is an x bar of size n equals 36. So we're adding up 36 different values that we're taking a sampling from the original distribution and averaging those 36 values and determining an x bar. So this is how we're determining our x bar. And if we imagine taking a sample size of 1,000, we would build a distribution, and what we will notice is that the mu of x bar of this distribution is equivalent to mu over, it's just mu, which is equivalent to 64. So hopefully you can kind of understand why this is true, but the idea is when you take so essentially what we're doing is we're taking the average of the averages, and we expect that average to be approximately 64. So you find one x bar of size n equals 36. It might be a little above 64, and then we take another x bar, a little below 64, and do this essentially an infinity number of x bars. You'd expect the average of all those x bars to be 64. So that's what this is saying here. And hopefully you can visualize that with the previous page of what we did. Now, sigma of x bar is equal to sigma over the square root of n. Now, this is equivalent to, in this case, 14 divided by the square root of 36. Okay? Which is equivalent to 14 over 6. And that is 2 and 1/3. Yeah, 2 and 1/3, so 2.3 approximately. Let's put 2.33 approximately. Okay, so yeah, so what we can see is that the original distribution, just kind of get a visualization, the original distribution which we're gathering the samplings from, or x bars from, it will be wider. And actually, what you may notice is that in the previous page, they told I told you guys that the original distribution is normally distributed. In this case, we don't even actually, we're not given that in problem 10. We're not given that the original distribution is normally distributed. But let me check something really quickly. What am I thinking? Yeah. Okay. But what we'll notice, actually, we'll get to on the next page, is that you may remember this from 243, is that we don't really care if it is normally distributed as long as n is greater than or equal to 30. So that's why I was able to use n equals 4 in the previous example, and we knew that was normally distributed. If we did not know it was normally distributed, the original distribution, and we only had an n equals 4, then we wouldn't have a large enough sample size to know that the sampling distribution is normally distributed. So keep that in mind, that you need to know that information. We'll kind of highlight that in a moment on the next example. So we have just determined sigma of x bar, 2.33, using the equation of sigma over the square root of n. Now, so the original distribution is actually going to be wider. Ooh, that's an ugly picture. But anyways, what you'll see here is we have mu equals 64, and a standard deviation away from the mean is 14 in the original distribution. We're still centered at 64 in the sampling distribution, so this is the sampling distribution. We will notice that one tick mark now is only 2.33. So the basic idea of this, if you haven't picked up on this already, is that when you're taking an x bar of a sampling distribution, and you're more and more accurate, and you'll have a smaller standard deviation as n increases. Hopefully that makes sense. X bar, like if you compare n equals 10, a sampling of n equals 10, and it's compared to like n equals 100, the n equals 100, you're going to be really, really accurate with your x bars because you're averaging 100 different values. So you'd expect x bar to not vary as much as n increases. So that's the basic idea. As n increases, your standard deviation decreases. And you can see that relationship here. So now let's go ahead and take a look at another example. So this would be the last example from this this section. And so this is kind of where we get into the central limit theorem. So the central limit theorem. So notice if the original distribution, I call this the original distribution, the distribution in which we're taking a sampling from. Let's say we don't even know what the distribution is. At least we don't know if it's normal. Let's just give an example of a distribution that's non-normal. The original distribution, let's just say it is a uniform distribution. Actually, let's make up a really ugly distribution. Let's just say we're taking a sampling from where we have 4 different possible values: 1, 2, 3, and 4. Let's say 1 has a really high probability of occurring. And 2 has a really small probability. And then 3 has a somewhat small probability. And 4 has a huge probability. Let's give some probabilities to these values. So let's just say 30% probability of this occurring, 45% probability of this occurring, so that adds up to 0.75, has to add up to 1, so let's just give this 0.1 and 0.25, or 1.5, sorry. So that adds up to 100%, and as you can see, this is most definitely not a, that is what a normal distribution looks like. That is most definitely not normal. This is non-normal. So what's interesting is, let's just say that we took a sample size of n equals 40 from this. So let's just say S1, our first sampling from this, we gathered up 40 different values from this. So the possible values are 1, 2, 3, and 4. Let's just say we gathered, we have a 1, we have a 4, we have a 4, 1, 2, 1. So as you can see, 2 and 3 are the smallest probabilities. So as you can see, I have more 1s and 4s so far. And then a 4, 4, and then you keep going until you have 40 different values, because we're taking a sample size of 40. What's nice is if you have a sample size of n greater than or equal to 30, then you know, you may remember this, but I'll actually talk about it in a little bit what this means. Notice it is greater than or equal to 30, because it's n equals 40. Let's just say we have x bar of 1. The x bar of 1, let's just say that this is 2.3. And then we take another sampling of 40 from this distribution, x bar 2. So this is just the first sampling we got our mean from. So we'll have an S2. We'll gather 40 values, take the average. Let's say this is 2.6. And then we have x bar 3. And that equals, let's just say 2.7. And x bar 4 equals 2.6, and so forth. And then we're going to continue this until we have x bar 1000. And again, I'm just choosing a really large number of sample means to gather. And so, yeah, so let's just say that's 2.65 or something like that. All right, so we've just gathered 1,000 different x bars, where each x bar was gathered from an n equals 40 to determine each x bar from this original distribution. What we'll actually notice is if we choose a large enough n greater than or equal to 30, then this sampling distribution will be normal. So sampling distribution, remember, is, in this case, since we're talking about the sampling distribution of a sample mean, each value in the sampling distribution is an X bar. So the first value is 2.3. The second value is 2.6, 2.7, 2.6. So we have 1,000 different values in here. So this is approximately what this distribution will look like. That's why I chose 1,000, a really large number. And it will be normally distributed with mu equals, or mu of X bar, the mean of this distribution, is equal to mu. In this case, we can find what that mu is. So mu, remember from Math 243, the expected value of x is equal to mu, which equals the summation of each of our values times the probability of each of our values, which is equal to 1 times 0.3 plus 2 times 0.1 plus 3 times 0.15 plus 4 times 0.45. Let's figure out what that is. You won't be doing too many of these calculations of finding the expected value using this equation in chapters 8 through 10, but it's needed in this case. Actually, I don't even think you'll ever use it in this chapter, but it's needed for this example. And the average happens to be 2.75 using the expectation formula, which is equal to mu. So this is equal to 2.75. And we'll, if you remember, the standard deviation is equal to, so the standard deviation is equal to the square root, if you remember from 243, of the summation of x squared times the probability of x minus mu, which we've already calculated, 2.75, squared. So this is equivalent to the square root of, all we have to do is square each of these values in the equation and substitute them in. So we'll have 1 squared times 0.3 plus 2 squared times 0.1 plus 3 squared times 0.15 plus 4 squared times 0.45. See how this equation is very similar to this? All we have to do is square each of our x values, 1, 2, 3, and 4, in the equation, and we obtain this first part of the radicand. And then we have to subtract mu squared, which is 2.75 squared. So let's calculate that really quickly. So this is all under the square root. Looks kind of goofy, but so what we'll end up getting is 1 squared times 0.3 plus 9 times 16 times 1.299. So that is equal to sigma. Remember, sigma is the standard deviation of the original distribution. And the standard deviation of the sampling distribution is equal to sigma over the square root of n. In this case, sigma over the square root of n is equal to 1.299 over the square root of n, which is 40. So each sampling, it's all based off of what each sampling size is to determine each x bar. So the square root of 40, and that I'll put approximately equal to 1.299 divided by the square root of 40. 0.205 approximately. So what we notice once again is that the sampling, remember this is called standard error, or standard error representing the standard deviation of the sampling distribution, is equivalent to 0.205, which is smaller than 1.299 for the same reason as mentioned before. It decreases in size as n increases. So each check mark is a distance of 0.0205 in distance away from each other. Okay? And the central limit theorem, the idea of the central limit theorem, if you look in your text, so it says regardless of the shape of the underlying population, in this case I'm calling it the original distribution, regardless of the shape of the original distribution, so it doesn't matter what shape it is, the sampling distribution of x bar becomes approximately normal as the sample size n increases. And the way that we judge if it's a large enough n is greater than or equal to 30. In this case, 40. So it's sufficiently large, and we know it's normally distributed. So that's the reason of having a large enough sampling size of n greater than or equal to 30 to obtain a normally distributed sampling distribution. Okay, so hopefully this is review for you. Maybe you haven't seen it taught this way before, but I kind of break it down so you can kind of see where it's coming from. Now let's look at another. So as the sample size increases, the central limit theorem says regardless of the shape of the original distribution, the sampling distribution will be normal, or will be approach a normal distribution as n increases. And that breaking point of large enough sample size is n is greater than or equal to 30. So just to sum up first off what we've talked about so far is if the original distribution, and I'm going to put this in quotes just to let you know, the text may not say original distribution, but it mentioned in the text underlying population. So the original distribution, meaning representing where you're taking your sampling from. If the original distribution is normal, okay, so it's normal, we know it's normal, then in order for the sampling distribution to be normal, we must have a large enough sampling size. Oh wait, but if the original distribution is normal, it doesn't matter what n is. We know that this is going to be normal. Normal always. It doesn't matter what n is. It's always going to be normal, the sampling distribution. Now, if it is not normal, we just break it into two different categories, normal and not normal, the original distribution. If the original distribution is not normal, then the sampling distribution, to be normal, we must have n greater than or equal to 30. Okay, that's what we've just determined with these two different examples we've looked at. All right, so if we would have looked at that weird distribution on the previous page and we only took a sample size of, let's say, n equals 10, then we would have noticed that if we would have plotted each those 1,000 x bars, that the shape of the distribution would not be normal. We have to have a large enough n, n greater than or equal to 30 for each of those x bars in order for the sampling distribution to be normal. Okay. Now let's go ahead and look at another example. I'm hoping to find one in which let's go ahead and look at number 27 from oh, wrong section. Okay, so Yeah, actually, let's go ahead and look at problem number 27 in section 8.1. And it mentions something about the Food and Drug Administration, FDALs. So, you're looking at the right one. It says insect fragments. So it mentions here, for example, the FDAL for insect filters peanut butter is 3 insect per 10 grams. A random sample of 50 10-gram portions of peanut butter is obtained and results in a sample mean of X bar equals 3.6 insect fragments per 10-gram portions. So, notice that part A just asks, why is the sampling distribution of X bar approximately normal? How do we know that it is approximately normal? And as you can see with all the information, that whole paragraph above, it never says that the original distribution is normal. It never says anywhere. All it says, is that that the peanut butter, well, from the information, you'll notice on number 27, just write it down, of section 8.1, all it says, if you pull the information out, is that mu is equal to 3 and sigma is equal to 10. Oh, wait. Actually, I do not see. Oh, it does say in part B that sigma is equal to the square root of 3. So it's not given up in the paragraph before. But in section part, so this comes from part B of section 8, number 27. But notice it never says anything about it being normal, the original distribution. But how do we know that it's normal? Because it says up in the paragraph that we're taking a random sample of size 50. So n equals 50, our sampling. And so since we took a random sample of 50, then this sampling distribution that this comes from is equal to, well, to answer part A, we know that it is normally distributed. Since n is greater than or equal to 30. Since n is greater than or equal to 30, we took our sampling from a size n equals 50, it's large enough. So we know that the sampling distribution is normal, even though the original distribution is not normal. Okay? So that is the answer to part A, because n is greater than or equal to 30. What is the mean? So part B, what is the mean and standard deviation of the sampling distribution of X bar, assuming that mu is equal to 3 and sigma is equal to square root of 3? Well, we know that mu of X bar, that's what they're asking for, mu of X bar is equal to, quite simply, mu. That's 3. And we know that that sigma of X bar is equal to sigma over the square root of n, which is equivalent to square root of 3 over the square root of 50, which is approximately equal to, let's calculate that really quickly, second square root of 0.245, approximately 0.245. Okay, so as you can see, like always, we've noticed so far, we know the square root of 3 is approximately 1.7 or so, and so notice getting an n equals 50, the sampling distribution standard deviation, or also known as standard error, is 0.245. Okay. So let's go ahead and, we haven't done this yet. Let's do it right here. what is the probability, part C, what is the probability that a simple random sample of 40 1-hour time periods result in a mean of at least 220 or 22.1 cars? So what is the probability? Now it's asking, pay attention to the wording. Oh, I'm looking at 28. Sorry. What is the probability that a simple random sample of 50 10-gram portion results in a mean of at least 3.6 insect fragments? So what is the probability that it's saying mean? What's the probability that the sample mean? It is at least greater than equal to 3.6. That's what it's asking. What's the probability that the sample mean will be greater than equal to 3.6? Well, we know that that is equivalent to, if you remember, we let's see here. So we haven't really talked about this yet, but the probability that something occurs, we know since that the distribution is normally distributed, since n is greater than or equal to 30, normal distributions, we can always, what we call reparameterize to a standard normal distribution with the z-score formula. So we can turn this x bar is greater than or equal to 3.6 to the probability that z is greater than or equal to, now you remember the z-score equation for a sampling distribution is 3.6 minus the mean. We know that the mean is 3, divided by the standard deviation of our sampling distribution, 0.245. So the probability that x bar is greater than or equal to 3.6 is equivalent to saying that the probability that z is greater than or equal to 0.6 divided by 0.245. 2.45. So that's the probability that z is greater than or equal to 2.45, approximately. Okay? So what this is saying, I mean, essentially is that x bar is greater than or equal to 3.6 is greater than or equal to 3.6 is equivalent to saying z is greater than or equal to 2.45 standard deviations above the mean. That's the definition of z. So 3.6 is 2.45 standard deviations above 3. Okay? And if we calculate this, we'll notice that that this is equivalent to, and if you remember, you can look this up in a z-score table, and this is equivalent to 1 minus the probability that z is less than or equal to 2.45, if you remember correctly. Now this is equivalent to 1, look this up in the z-score table, at 2.45, and we want less than or equal to, because that's what the z-score table tells us, if you remember. This is equal to 1 minus 0.00 or 0.9929. We'll find that under the z-score table. 1 minus that is equal to 0.0071. So, and it also asks, is this result unusual? Remember, unusual occurs when it's less than 5% probability. So as we can see, it's much less than 5%. So it is very unusual to have a x bar greater than or equal to 3.6. Okay. So all right. So anyways, that's just a quick example of how to find the probabilities, a quick review. And in regards to some equations that you may want to use, from your calculator, just a quick review. There's the normal CDF function. The normal CDF function will help you find a probability given some given information. So normal CDF can be found at under second vars. So this can be found under second vars. Okay, and you'll notice it's the second option if you have a TI-83. So normal CDF. And then what you can do is you'll put the lower bound, upper bound, mean, and standard deviation. Okay? And we want the mean and standard deviation of the sampling distribution. So more accurately, we would want X bars here. Okay? So that, in this case, let's just check our work with part C from the last example. And we want to find the probability that X bar is greater than or equal to 3.6. That's the same thing as saying greater than or equal to 3.6 would be normal CDF of 3.6 to upper bound is greater than or equal to 3.6. So you can keep going up forever. So it's safe to just say something like 10,000 or 100,000. Okay. Don't put a comma there. Actually, that doesn't. The calculator won't like that. So 100,000, and then we want mu of X bar, which is we know is 3, and 0.245. Okay, because that was the standard error. And we'll plug this into our calculator and see what we get. So normal CDF of 3.6 divided by 100,000, not divided by, comma. There we go. And then 3, comma, 0.245. So, can you see what I have here? So yeah, you can see normal CDF of 3.6, comma, 10,000 or 100,000 or whatever I've written there, large number, comma, 3, comma, 0.245, and that equals 0.00763. Anyways, if you remember, that was approximately our answer. So that's what we had in the last page, 0.0071. Just a quick review of how to do this on the calculator. All right, so anyways, that kind of concludes section 8.1. You can go to the end of the section of section 8.1, and it has kind of a summary on the bottom of the page right before the exercises starts, and it kind of summarizes everything we just talked about. And just to show you really quickly what that looks like. This is what I'm talking about. You might not be able to see it, but you can kind of see what I'm saying here. It'll look something like that. And it kind of summarizes everything we just said about the shape. If you know the original distribution, we know that we need a large enough n. And, yeah, from a normal, non-normal. And we have the same parameters, center and spread, mean and standard deviation of the sampling distribution. So that's section 8.1. Maybe a little bit too much information, but I wanted to kind of give you my perspective and how I think about it, and kind of just how things work in my mind and how I was introduced to it in school. Anyways, let me know if you have any questions, and you probably have more than enough information to do section 8.1 questions. All right.